that different models give different AZ, but it is very different from what lambda CDM gives. But one thing we have tested from here, that if you take for any point Hz minus H0 by H0, then it remains more or less same, it is 0.19 or something for all the three models. Hz minus H0 by H0 at any redshift z comes around 0.19 or so. I do not know what is the significance of this, but this is an observation. Now, what are the equations that has to be solved? I am not going to explain these equations. This is just some statements I will make. This dt by dz, I mean dz means how the temperature of the dark matter, but here I must say that dark energy and dark matter collision, when we consider their dark energy and dark matter is considered to be fluid. And the scattering of dark matter with the baryon, there is another kind of dark matter beam, but those are particle dark matters. So that dark matter temperature evolution is given by this kind of equation. This is easy to write. If you do dt by dt time, that means you express it to be t, then these terms will not be there, as you know from postology. The temperature evolution of baryon is the gas temperature, is this. And free electron fraction is also required because there are compound scattering that can produce heat, etc. So free electron variation with Z is given by this. And there can be dark matter baryon drag. That means if dark matter has some velocity in the baryon fluid and the dark matter fluid, they will drag, and that depends on the relative velocity v of the dark matter and baryon. And so this is the drag term, and this is the relative velocity term. That is the evolution of that also has to be taken into account. So these are the equations along with the previous two equations, which are all coupled, these many coupled differential equations, which are to be solved to obtain this baryon temperature or gas temperature. And when in thermal equilibrium, the gas temperature becomes the 21 centimeter temperature, T21. So this is how this is what has been done actually. And there are certain things it is not very relevant. All I said is, but these are just taken from this paper. That's why. So these are the results. Delta T21 means the 21 centimeter temperature. This is the 21 centimeter temperature. What we calculated or computed from all those 6-7 coupled differential equations minus the T21 measured by the edges. Now, edges has given a big range, minus 300 to minus 1000 millikelvin. Here we have taken only minus 500, the mean value. Minus 500, whatever, minus 500, here is the mean value. So minus 500 millikelvin has been taken, and different m chi, the mass of the dark matter, is taken. And this one is with lambda, and this straight line is So the edges limit is for delta T21 is given by within these two things. So only these two plots corresponding to sigma 41 means the cross section expressed in 10 to the power minus 41 centimeter square, the scattering cross section of dark matter and baryon. So that is expressed in 10 to the power minus 41 centimeter square, which is well within the ballpark of this direct dark matter experiments. So this one and this one, no collision, and just this collision of dark matter and baryon satisfies, partly satisfies. This one also not satisfied. So at least from this, it is for m chi is equal to 0.1 GeV. At least the dark matter baryon scattering plays a role to explain, at least to a certain extent, the gauge's 21 centimeter result. Here also, below this line is the edges limit, And here you see some other sigma 41, I mean the higher values of sigma also allowed for m pi is equal to 1 GeV. And for 10 GeV similarly, this one here, below this is allowed actually. Okay. And this one is that same delta T21, that means 21 temperature computed minus 21 temperature measured, 21 centimeter temperature measured with lambda, varying lambda. This is to check which model actually, for all those three dark energy models, there's cube, etc., which model actually fits best. So that exercise is done, and it is okay. This one is different than the last slide actually, but this shows that the model 1 is efficient. I mean, it is with in sync with the 21 centimeter results, but model 3 and model 2 are not. So this is the, and then this is the last slide, and no, there is one more slide also. I think, yeah. This is with sigma is equal to 10 to the minus 41 centimeter square. This is the scattering cross section, I repeat. What is the allowed zone of the dark matter mass and the dark matter dark energy coupling that satisfies the HST 21 centimeter brightness result by edges. So you see, this is a allowed region. So I mean, as the mass is increased, the lambda is also increased. But we know that lambda from one model gave lambda as 0.1. So in that we get around 1 to 3 GeV mass of the dark matter. So the collision has to be made with a 1 to 3 GeV dark matter. Later there is a later allowed region we have tried to plot, which is with the cross section. We vary the cross section and the dark matter mass. And for lambda is equal to 0.08 or lambda is equal to 0, in both the cases you see the mass does not go beyond 10 GeV. So actually it is expected that the other papers also quotes that the mass of the dark matter such that the dark matter baryon collision is incommensurate with the T21 temperature will be around 1 to 2 GeV. So this 1 to 2 GeV is within the allowed region here actually. So this also we got. So I think I came to the end of this. What is that? Okay. Yeah. There is some comments that is made here. And so first is the AGES experiments has observed an excess drop in the brightness temperature. So to explain that, could not be explained by other astrophysical phenomena. So we try to explain this by taking into account the baryon dark matter interaction and dark matter dark energy interaction. And we find, of course, I forgot what is written here, but what I am reading now, I am telling that we have found that the dark matter mass is to be in the ballpark of 1 to 3 GeV, and the dark matter dark energy interaction strength should be around minus 0.1 or 0.01, I think 0.1, which is given by one of the models by other authors. And what is there? Model is considered, yeah. DMD interaction raises the possibility, no, there is some typo here, possibility that photons of probing larger mass range of DM that could have influenced the cooling effects. So I think this probably, yeah, this is what.
Thank you, Devasis, for completing your talk well in time. And next now for questions. And Subir.
Has the edges signal been discounted by the Indian experiments?
Yeah. I mean, but whatever I found that ISCB or the RRI people, they very forcefully claim they have discarded, but still a consensus, worldwide consensus is required that it is not. So on that I have done.
Concerns about the result, about the SARS results?
No, they have told that it is wrong, AGES measurement is wrong, but what is right that they haven't told? I mean, what we should get. We should get minus 200 millikelvin or minus 300 millikelvin. That is wrong, okay. But what we should
The
have.
point is that the sensitivity is not enough to say, because
Yes.
it's a huge electric photon that is subtract around 50 megahertz, and when you do that, you cannot actually take the segments which are adjusted. We
No.
can discuss later.
Yeah.
Any more comments? Question? There you go.
I did have a question which might now be moot given Cynthia's comment, but if indeed you want to blame it on dark matter interactions, there are of course rather strong limits on how strong dark matter can interact with baryonic matter, or dark matter from increased. The range of your parameters, is that consistent with the constraints on the possible strength of the dark matter?
Yes, very much actually. But one thing I must say here, this dark matter mass that is being constrained to
Not on the mass interaction, the interaction strength with normal matter.
interaction strength, yeah, that is consistent with, because that.
That's consistent with the current constraint.
Yes, because there are a lot of this dark matter, the direct detection experiment is going on. They are based on the dark matter nucleon scattering.
Yeah, but no, also from the evolution of the universe, there are constraints from
From the.
for the dynamics of galaxy rotation. So, so it's called dark matter because the only clear evidence is gravitational interactions. But I don't know what the limits are on any other non-gravitational interactions.
Yeah, there are limits of the dark matter interaction with other baryons or other nucleons or nuclei. I mean, that limit is respected here, yeah.
Well,
So, Saras group already published their paper with more than 95% confidence.
Right.
And the Aegis group accepted that there were some problems.
Yeah, I know that. But still, what I am saying that I didn't find what would be the result. That must be what Sumita is telling. There should be the sensitivity issue and all. But still, there are some worldwide consensus, more widespread consensus is required. I know that they have said that it is being accepted slowly, but still there are. I mean, what I feel that more widespread consensus is required to come to the conclusion. No, this is wrong, and we should not work on this. Actually, this kind of. Perhaps it will come.
We should work on this, but
Yeah, for this not with this result actually.
Thank you.
any more question? Let's not. Let's thank Devashish again and we wait for